So welcome to this webinar organized by the ISPRS Working Group Commission 3. So I'm very happy to introduce Michael Schmitt, who is a very renowned scientist of our community. So maybe just a few words about him. So he obtained a PhD at TUM, and then he was senior researcher at Signal Processing in Earth Observation Lab, a joint venture between TUM and the German Aerospace Center. And then he has been professor for applied geodesy and remote sensing at Munich University, and now he is full professor for Earth observation at University of the Bundeswehr Munich, and he is the head of the Earth observation lab here. So, Michael, I think you will talk about very, very interesting things on SAR imaging and so forth. So the floor is yours.
Thank you. Let me quickly share my screen. Yeah, thank you, Florence, for the kind introduction. As you can see from the name of my talk here, Deep Learning for SAR Image Analysis, I will talk about something very similar to the talk given by my dear colleague Florence a few weeks ago. But everybody who has visited her talk can still stay, because I will approach the topic from a slightly different angle. So you will still learn something new. So what will I talk about today? First, I will, as an introduction, very quickly recap a little bit the application of deep learning to remote sensing problems. Then I will focus on the peculiarities of SAR data. And this brings me, or will bring me, to the main part of the talk, namely the task of height reconstruction from single SAR intensity images, which I will use as a very nice example or use case of deep learning applied to SAR data. I will, of course, provide you with some nice pictures, some slideshow of nice example results before summary and conclusion is being drawn. So now, without any further ado, let's jump right into it and let's talk about what's up with deep learning in remote sensing. And I want to make a bold entry statement here, namely saying that many of the deep learning applications in remote sensing have exactly one thing in common. You have as input an image and as output again an image, or an image-like piece of raster data of the same resolution. I've shown here two examples. In the first row, we have the classic case of semantic segmentation for land cover classification. So the input is an image and the output is a land cover map of the same resolution. Another example is image-to-image translation. In this example here, the input is a SAR image and the output is a pseudo-optical image. And of course, you can extend this also to many other tasks. For example, for pixel-wise soil moisture estimation, or pixel-wise biomass estimation and other things like that. So many of the tasks in deep learning for remote sensing are this style. And how is this typically being done? Well, there is one model to train them all. If you look into the literature, one of the most popular architectures to solve such tasks is the UNIT. The UNIT, I'm pretty sure everybody listening to this talk knows it, has been invented about 10 years ago by a group of German computer vision scientists from the city of Freiburg. And as the name already suggests, it's a deep convolutional neural network of some U-shape, and the left part of this U-shape is the so-called contracting path, and the right half is the so-called expansive path. And the whole idea is to take an input image and to downsample it to learn about its salient features and create some sort of meaningful latent space representation, which then in the expansive path is again let's say inverted, so that the output product you want to have is reconstructed via upsampling operations. And then one of the nice features of the unit are these arrows here in the middle, the so-called skip connections that are also found in ResNet architectures that pass through spatial details, so that you really end up with an output product, map, image, whatever, that is of similar visual quality as the input image. So this is a very famous architecture. Again, I'm pretty sure everybody knows it, but I wanted to bring everybody on the same page here. Now, this unit is really enormously popular. The original article has meanwhile been cited more than 100,000 times. This is really amazing. There's only few textbooks that are cited as often. So great work by the Freiburg colleagues. And also in remote sensing, you have really hundreds and hundreds of publications that use variants of the unit for many applications, from land cover classification to biophysical parameter regression. I've here done a very quick Google image search, unit remote sensing, and this is a very small and very random selection of unit variants, or let's say of figures about unit variants published in different remote sensing papers. Yeah, so really this is what pretty much everybody is using these days. And if you look at the new literature on foundation models, you very often see in benchmarks that units are still quite capable, even in comparison to modern transformer architectures and foundation model architectures. The unit just is a really great model. Now, if this is such a great model and all the tasks are very similar, why don't we just take our SAR images, put them into a unit, and get things done? Well, let me tell you that the whole talk will be about why this is not the final solution, and this is mainly because of the peculiarities of SAR data. Because in the end, the hypothesis is it's a bit harder to work with SAR data than with classic everyday computer vision imagery, and also still it's more complicated than using electro-optical satellite imagery. Why is that? Because SAR data are special. And therefore, SAR data analysis is not the same thing as classic image analysis. First and foremost, we don't passively collect reflected sunlight, but we actively illuminate the scene with our radar system. And therefore, we don't count photons, but we record amplitude and phase of the received signal. And that already means if you really do it in the correct way, we have to deal with complex numbers instead of real valued measurements. So this already is a big difference. Secondly, and I will talk about this a bit more on the next slide, we have to face non-Gaussian statistics due to the so-called speckle effect. So whereas optical images pretty much give us nice digital numbers simply based on photon counting, and are typically normally distributed, here we have to deal with non-Gaussian statistics. And then also we have not typically a near-nadir viewing geometry like in optical imaging, but an oblique observation geometry, which we need to be able to resolve targets at different range. And finally, we don't have angles as primary measurements, but ranges. And all that really makes SAR images greatly different to optical images as input to deep neural networks. Let's start with the radiometry. I mentioned it already. We have the situation that for every SAR data take or SAR data matrix, we have two primary pieces of information. Here, the foreground layer is the, in this case, amplitude image, could also be the intensity image. And here in the background, we have the corresponding phase image. And if we zoom into the amplitude image a little bit, for example, here on this homogeneous patch of grassland, we see that we don't have a homogeneous gray value like we would expect in optical images, but we have this granular appearance, we have this mix of dark and bright pixels. And this, of course, is not noise, but it's the signal. And this signal is, there are different interpretations, but a common one is it's Rayleigh distributed. And this is really based upon statistical modeling. This is not noise, it's just within the coherent signal. And the second image here in the background, as you see, doesn't carry any meaningful information. It's the phase, and this phase is uniformly distributed. So here again, we have a very special radiometric appearance of SAR images, which is much different to optical data. And this is also why it doesn't always make sense to use models pre-trained on optical images to analyze SAR images. Even more important than that, in my point of view, is the geometric peculiarities of SAR images. And this really comes into play mostly if you work with complex scenes, such as urban areas, and with very high resolution data. The problem is not as prominent if you work with, for example, Sentinel-1 imagery of medium resolution and maybe rural areas, then you can almost ignore this. But if you take cutting-edge high-resolution data and urban areas, then you really have to take this into account. And here we have two main issues to address. First thing is, because we always have this oblique viewing geometry, elevated structures, here buildings, appear as if they collapsed towards the sensor. So they seem to lie on the ground and not stand upright. And this already is a bit of a problem. But secondly, the extent of the so-called layover, so how long is the building that lies on the ground or seems to lie on the ground, strongly depends on the so-called off-nadir or incidence angle theta. So here on the left, you have an off-nadir angle of 47 degree, on the right of 21 degree. And as you see in the sketch here in the middle, this layover extent, so the extent of the building seemingly laying on the ground, is much shorter for more shallow or larger thetas than for more steep or smaller thetas. And for the so-called radar shadow, so occluded parts in images where we don't have any information, it's exactly the opposite or vice versa. So you see, for example, here in this left image, behind this factory building, there is a shadowed part. So we have to deal with this layover and shadowing phenomena, which are strongly incidence angle dependent and really make a one-to-one mapping, for example, between SAR and optical data impossible. And therefore, to summarize until here, we can say many remote sensing tasks can be tackled with deep learning, and this is really being done avidly or has been done for about 10 years. The UNet is a very popular and powerful choice for many semantic segmentation and regression tasks, any task where the output is more or less similarly resolved as the input. And finally, SAR data are not images, but complex measurements with physical meaning. And therefore, the hypothesis of this talk is that SAR expertise must be combined with modern deep learning approaches for the best results. And I will illustrate this using height estimation from single SAR images as example. And now we go right into the middle of it, height reconstruction from single SAR intensity images. And I will start with what we coined the SAR to height approach. First, let me give you a little bit of background. So in computer vision, many years ago, scientists have started to develop approaches framed under the umbrella term single image depth estimation. This is a very prominent and important task in computer vision because it has lots of implications for robotics and for autonomous driving and fields like this. Always with cost efficiency and speed in mind. So instead of using two cameras or needing two cameras for triangulation, you just want to use one camera and still infer depth and get information about the 3D structure on the environment. In remote sensing, researchers soon started to apply the same principle, but here the big problem is that our target is not depth. That means some distance relative to the sensor, but height. And height is always something that is relative to some invisible geodetic reference. So I'm a geodesist by training. You can hear a full semester's class on heights and height systems. You can have heights above mean sea level. You can have heights above the ellipsoid approximation of the Earth. You can have heights above a digital terrain model and many other things. Height is very, very relative and not relative to the observer or relative to anything you can see or easily measure, but rather to something that you can't see. And this is a big problem. The second problem is that whether it's a single image depth estimation or a single image height estimation, you are looking at a mathematically ill-posed problem because you have 2D information, a two-dimensional image, and you want to get 3D information. It's like solving a linear equation system with three unknowns and two equations or two observables. That's not enough. It's mathematically not tractable generally. And finally, labeling is also an issue. In the optical case, it's relatively trivial. So look at the top example here, if you have this optical image in near nadir viewing geometry on the left, and this digital surface model here on the right, everybody can use some GIS software off the shelf and do a co-registration of the two data sets, and you have your annotated data set, no worries. But in the SAR case, it's a bit more complicated. If you have a SAR image in this original native slant range geometry, then you have to reproject your digital surface model into what the SAR is actually seeing to make ends meet and to make a pixel-wise annotation. So here also a bit more engineering effort has to come into play. We started to work on the whole problem scenario around 2021. And in 2022, we finally were able to publish our first paper in the ISPRS journal, which was basically merely a proof of concept illustrating that it's possible to infer height using deep learning from single SAR intensity images, and we used a standard UNet for that. So here, maybe to self-confirm my hypothesis earlier, UNets are really a go-to solution. Then we continued the work and we faced a rather long review cycle, but in 2024, we were able to publish our SAR to height method, really an end-to-end framework that really gives you well-calibrated digital surface models. And here again, we use the UNet, but with an add-on called metadata infusion block. I will talk about this later. Shortly after that, we came up with SAR to height dual, another UNet with this metadata infusion block and two input branches as an extension of SAR to height. And I'm very happy that for SAR to height and SAR to height dual, we received lots of support by Airbus Defence and Space to carry out our research and development activities. And now in 2025, we came up with what we call the SAR-former or SAR to height SAR-former. This time it's a vision transformer with parameter tokens, and it's now our latest development. And interestingly or funnily, it's presented right now, this week, in the context of CVPR in Nashville. So my PhD candidate being responsible for this work is right now in Nashville and presenting the SAR-former on the Earth Vision workshop at CVPR. Now, let's start with the SAR to height framework, this UNet with metadata infusion block, to give you a few insights about how you can pair SAR expertise with deep learning to create efficient models. The overall framework is like this here. It's very typical. Everybody knows this. You have first a training stage and then an application stage, or here called evaluation stage. And what happens in the end, I pretty much want to show it's not all deep learning. There's also a lot of pre and post processing that needs domain expertise. So if we start in the training stage here, what we have is some input data in the SAR native slant range geometry and some digital surface model as, let's say, target or ground truth. That has to be projected into this SAR view to generate this projected annotations and to pair these images with the projected height data. Then in order to fit the stuff onto GPUs and do mini batch processing, you have to slice everything into patches, and then you can train your supervised model, in our case, the improved UNet. You get your model parameters, and later, if you want to apply your approach, you take some SAR input data, again in the native SAR native slant range geometry, you slice it into patches, and because we have this metadata infusion block, you can extract some extra metadata and put it inside here. You will get an estimated normalized digital surface model, so heights above ground in slant range geometry, and by adding this to a globally available digital terrain model, you can geolocate every pixel and receive a 3D point cloud. And this point cloud can then be rasterized and filtered, and then you get your final digital surface model on ground that you can store as GeoTIFF, for example, and use for other tasks. But of course, the most interesting part here is the UNet, so the deep learning part. And as I said, it's a fairly standard UNet, of course, with some adaptations. I mean, I don't talk about the minor changes such as input size or dimensionality or output dimensionality. But what really has to be changed is, of course, you have to replace the binary semantic segmentation output and cross entropy loss for a regression output and mean square error as loss. Then we added some multi-scale res blocks like we found in other literature. And then the main addition here is the so-called metadata infusion blocks that are shown here in purple. And these metadata infusion blocks, they are add-ons to conventional residual blocks and are basically designed to allow us to add n auxiliary scalar values into the network and giving the model the chance to decide where to use this information and where not to. So it's going a bit beyond simple band concatenation. There's also some concatenation involved, but it's a bit more complicated, giving the model a bit more flexibility how to make use of these n scalar auxiliary variables. And in our case, what did we use as auxiliary variable? You probably have guessed it already. We used the local off-nadir angle theta, because as shown before, this is the one parameter that most significantly influences the appearance of buildings and elevated structures in high-resolution SAR imagery. And now, of course, we have to train a model. And at that time, in 2021, 2022, 2023, so in the beginning where we developed the SAR-to-height framework, we gradually built up our training data set. And we were happy to get lots of images from the German Aerospace Center and later also in our collaboration with Airbus from Airbus. So we built a data set based on very high resolution TerraSAR X images in two different acquisition modes, namely high resolution spotlight and staring spotlight with incidence angles ranging from 20 to 53 degrees to have some diversity in terms of incidence angles. We used 7 different and more or less globally distributed cities for training. If you look closely at the names, it's not really globally distributed, but we tried our best. And then we reserved one city as a holdout test scene that was never used in any training, and this is Berlin, Germany. Overall, at that time, we used 51 SAR images for training, and the annotations came from LiDAR that had to be projected into the SAR geometry, of course, for training, but was remaining in the original UTM map geometry for evaluation. And now what you're really interested in is, does this metadata infusion block, so our changing of the original unit architecture, bring any benefit? And for this, we can look at this result. We have a SAR image here, and we have some transect going from A to B, looking at one building here. And you see in the second picture, the LiDAR ground truth projected into this SAR slant range geometry. And then in the third column, you see the SAR-to-height output without the metadata infusion block. And in the last column, the SAR-to-height output with the metadata infusion block. And a quick look at these two result images already shows, at least to me, that the final image, the fourth image here, is a bit smoother than the result achieved without the metadata infusion block. So this is my first impression. But then if we look down here at a side view of the transect profile from A to B, we have in the brownish foreground color the LiDAR ground truth profile. Then we have in red here the curve or the height distribution that was predicted, the height profile that was predicted by SAR-to-height with metadata infusion, and in blue without metadata infusion. And I think you will agree with me that the red curve is much closer to the brown curve than the blue curve. So apparently, from a visual point of view, there is an added benefit. And the same is also observed in this table, showing different metrics like root mean square error, mean absolute error, and structural similarity index, where in any line or in any box, the model with the parameter injection provides significantly better results than the model without this parameter injection. So here, maybe this is the first soft proof that pairing deep neural networks with a little bit of sensor expertise can already help and provide better results. Now let's come to the second approach, SAR-to-height dual. If we look again at this development timeline, this was the model that came out in 2024, a unit with the metadata infusion block and 2 input branches. Why did we bother with that? Why did we continue this way? Because some challenges were remaining. And I want to show you these challenges at these two real-world images shown here. We have a very famous city. I presume everybody will recognize it. It's Paris in France, with the Eiffel Tower prominently in the center of the image. And we have two SAR images here, once in descending orbit and once in ascending orbit, so opposing viewing directions. And you see that in the leftmost column here, the Eiffel Tower falls into the same direction in both images, namely to the left, because this is the viewing direction of the sensor, or the opposite of the viewing direction of the sensor. But then if we geocode those images, so we transform them to lie in, on the Earth's surface in ground range coordinates, then the Eiffel Tower in the descending image falls to the right, or roughly to the east, and in the ascending image to the left, or roughly to the west, because we have opposing viewing directions, so we have opposing displacements caused by layover. And then if we look at the 3D reconstruction, single image based, in map geometry, we see that this Eiffel Tower is a very elongated, very elevated structure, occludes several smaller buildings on the right here in the top result and on the left here in the lower result. So what do I want to say? Elevated objects will occlude lower objects behind them, and also if you have results from different angles, they don't necessarily fit together. And this is also observed here in a more simple sketch-based way. Here on the left, we have the scenario again. If we have opposing views, the blue radar beam, so to speak, can observe both buildings, the lower one and the larger one, but only the sensor-facing facades and the roofs, whereas the red radar beam can only observe the larger building because the smaller building behind the larger building is totally occluded, or the view is totally obstructed by the larger building. So you will end up with gaps in your data, and the data doesn't necessarily fit. And then comes another problem, namely, of course, predicting 3D information from 2D images as ill-posed problem can never be perfect. Our deep neural network can never give us absolutely perfect results. And if you have a small height error, delta H here, this will project into a localization error, delta X, on the ground over the cotangents of the off-nadir angle theta. So once the model makes a mistake in height prediction, which it always will do, you will also mislocalize your 3D information on the ground, and that of course deteriorates your results. And therefore we came up with the idea, let's perform height reconstruction not in slant range data, but in geocoded imagery, and let's combine two opposing views in an end-to-end fashion to do some sort of data fusion to get a better, more reliable, more robust result. And that's how we developed SAR-to-height dual, which is shown as a flowchart here on the left. The flowchart is super complicated and we don't have to look at it in detail. In particular, we ignore the pink box up here, because this is only telling us how to reconstruct rational polynomial coefficients that are typically used in optical imaging for SAR data. But what we really need to know here is, we start with the globally available digital terrain model and with the image data from the ascending view and the descending view, and we use rational polynomial coefficients, or if you want, metadata about interior and exterior orientation, to project these image data onto the digital terrain model before any deep learning. And then we put the geocoded images into the model to carry out height inference. And as model, we use the same unit as before with one slight change. Namely, we have now two input branches that process the SAR images simultaneously during training and inference. And we could call these pseudo-Siamese input branches. Yeah? So there's lots of architectures that use pseudo-Siamese architectures, basically meaning that the branches have the same structure, but the weights are learned independently. And this is a slightly different approach. The question now is, are these adaptations any useful? Well, look at the result with me and judge yourself. We have on the upper left here single image height reconstruction using just one view from ascending orbit. We have down here just one view from descending orbit. And then we have here in the middle a SAR to height dual reconstruction. And if you look, for example, at this big building here, then you will immediately see when comparing the three results that this is by far the most accurate and most complete result. And also the building outlines are much, let's say, more clear than in the single image results. Here on the right, we have the ground truth again. Of course, we don't reach fully LiDAR quality, but this is also not expected. But we come much closer with our dual approach than with the individual single image approaches. And now let's come to the final development, SAR to height, SAR former. Again, coming back to the timeline. Now, this is very fresh, hot off the press. A preprint has been available for a couple of weeks. The official paper is published this week. And yeah, this is now, from our point of view, the new gold standard here, a vision transformer with parameter tokens. Why did we do that if the other models work already quite well and if the unit is so good? Well, as shown before, results strongly depend on incidence angle and viewing direction, but these are not the only parameters influencing the mapping of urban environments to SAR intensity images. Also acquisition mode, spatial resolution, sensor calibration in terms of gray values, etc. are also very, very important. And if you really want to train a globally applicable model that can deal with any SAR images, you need a huge diversity of data in your training set. And that also means you need really huge data sets to capture all possibilities. But we all know high-resolution SAR images are typically not free of charge. They are very expensive to procure, and they are certainly not globally distributed because they are typically only acquired over scenes of commercial interest. And therefore, this is not really a go-to solution to create an enormously big high-resolution SAR image data set. So we thought, okay, let's rely on a so-called vision transformer architecture. And then we invented some new metadata tokens to support the vision transformer. And let's combine this with self-supervised pre-training to create powerful models. And this led to the SAR former, which is illustrated here on the right. What is the nature of the SAR former? Again, it's a vision transformer with multiple inputs and multiple outputs. The inputs are n SAR images acquired in arbitrary modes or angles, plus information about the imaging mode, the incidence angle, and the azimuth angle. As it is right now, of course, it can be extended arbitrarily. The generic concept is extendable, but this is how we did it right now. And the output in a multitask learning fashion is height maps in slant range geometry, the heights in the UTM map projection, and a building footprint mask. This is a new add-on here. And to see this illustrated here on the right, to give you an example, we have, for example, view 1, a strip map image with an off-nadir angle of 43 degrees and an azimuth angle of 280 degrees. And the second view is a staring spotlight image, so totally different quality and resolution with an off-nadir angle of 35 degrees and an azimuth angle of 80 degrees. And you see these images hardly have anything in common. They only show the same city, again, Paris, but they are really totally different. And the output of the SAR former model is then the two independent height maps in the original SAR geometry, plus what we really want, the height maps as a digital surface model in top view if you want, and a building footprints map. And if you render the result, you end up with a nice illustration like this here. And what's at the core of the SAR former architecture? Again, it's this vision transformer. And due to lack of time in this webinar, I won't now explain the whole principle of transformers or vision transformers, but I presume everybody knows these days that transformers are designed in the first place to deal with sequence data. And a vision transformer basically uses this principle by splitting an image into patches that are then treated as sequences as in the form of so-called tokens and can be processed then, and in the end they are recompiled to images. And while we have these tokens, TI, that represent the image as sequences, we have also added so-called metadata tokens that carry the meta information. So the acquisition mode, the azimuth angle, the off-nadir angle, and so on. And these tokens are then passed through different modules to be fed into an encoder network, and then to be decoded again. And what we see up here is the pre-training stage. And I will talk about this on the next slide a bit more, but this is not happening with labels, but with the concept of self-supervision. And later, you take the weights of the vision transformer that you have trained during the pre-training stage, and you add eventually a so-called multitask head that unfolds the tokens from the encoder network into the desired end product. So in our case, as mentioned, the heights and slant range geometry, the heights and ground range geometry, and the building footprint map in ground range geometry. So the main magic here is, on the one hand, the self-supervised learning, and on the other hand, these metadata tokens that make the model aware of the conditions, the boundary conditions under which the data were acquired. Now, a few words about the self-supervised pre-training. This is also a very hot topic these days, so probably also many people have worked with it or know already about it, but again, to bring everybody on the same page, self-supervised pre-training offers a very powerful possibility to train features, powerful features, without any labels. And the supervision task that's typically used for vision transformers and in remote sensing is the task of image reconstruction. You see this here on the right. If we say, okay, our n is equal to 2, so we use 2 views to put as input into the vision transformer, then you can follow, for example, 2 styles of masking for image reconstruction. The first one here would be blind channel image reconstruction. So here, to simplify it a bit, the task would be to reconstruct the view 2 from the information provided by view 1 plus the metadata information, so the acquisition mode and the angles. The model is basically forced to learn powerful features to transform this view 1 image data plus the meta information into this view 2 when knowing view 1 and the 6 meta parameters. And another option would be random masking, where both images are generally available to the model, but they are randomly masked in a patchwise or token-wise manner. And the task then is to infer or to reconstruct the missing patches by the information provided in a complementary fashion from the 2 views and the metadata information. So you can realize, I believe, that with this self-supervised learning strategy, you can, on the one hand, use lots of data for which you don't need expensive and hard to get by labels. And you can really make the model very powerful in terms of understanding how does a certain SAR image look, what does it look like, given the acquisition mode, the incidence angle, and the azimuth angle. This is more or less the magic here. And the effect is that models become more powerful, more robust, and can get trained much faster. And then for your downstream task, in our case, height estimation and building footprint estimation, you need only fine-tuning, for which you need much less training data. So you can save lots of money here and lots of effort. Again, I want to show the benefit of the SAR former, and maybe let's start by looking at the images here on the right half of the slide. We have a high-resolution SAR image, in this case strip map mode, ascending orbit from a harbor area. You see the same harbor area here in an aerial view extracted from Google. And if you apply your standard UNet, so not really our SAR to height framework, but a standard UNet, this is the height map you get as a result. Here you see the SAR former trained from scratch, so without any pre-training. And here in the lower left, you see the SAR former with pre-training involved. And in the lower right, you see the LiDAR-based ground truth. And if you compare, especially the buildings here in the red box, then you see that in the classic UNet case, but also in the SAR former from scratch case, the buildings are not perfectly reconstructed. So there's height deviations within a single building. And especially in the unit case, all the outlines of the building are not perfect. But if you use the SAR-former pre-trained, then you have very crisp building outlines, and also the heights match very well the heights in the LiDAR ground truth. And also this I don't know, star-shaped structure here is quite well reconstructed in the pre-trained SAR-former case and not so well in the other two cases. And the same is basically also repeated in these complicated tables here on the left. So if you use the parameter module and if you use pre-training, you end up getting the bold numbers here in the tables. So also quantitatively, we can confirm that a pre-trained SAR-former network is beneficial and superior to the other networks at hand. Now I have guided you through the development story of our different SAR-to-height models, from a simple unit to unit with parameters, to a vision transformer with parameters and self-supervised pre-training. Now it's time to show you some actual example results that go beyond these ablation results. And for that purpose, I finally use a TerraSAR X high-resolution spotlight image of the city of Berlin, Germany. As you recall, holdout city. You have the Park Tiergarten here. You have the Berlin Central Station here. You have the Spree River here. So people who know Berlin will recognize the structure. And this was the input at test time or evaluation time to our models. This is the LiDAR ground truth. So we start first with the so-called gold standard, a model you can acquire with an aircraft flying some, I don't know, 300 meters above ground level. And this is very costly, but also of very great quality, and it's typically done by the surveying administrations of municipalities or state governments. This is what you would buy if you really want highest quality data to do, for example, a digital twin of a city, or a digital city model for visualization purposes. This is one thing that exists, and you can buy. Now, a second thing that exists is the Tandem X World DEM. So we are here in the ISPRS working group of microwave remote sensing. So SAR experts are in the audience. Everybody should know the Tandem X mission carried out by German Aerospace Center and Airbus Defense and Space. Companion satellite mission carrying out single pass interferometry to produce a global digital surface model from at least 2 coherent INSAR acquisitions and well-established SAR interferometry techniques. Of this raw world DEM, the resolution is 12 meters, and this is the same city. So this is the product you can maybe not exactly the product, there's some manual refinements, but this is the basis of the product you can buy at Airbus if you want the current gold standard of global digital elevation models. If you want to have a globally homogeneous elevation model, this is the only thing you can pretty much buy right now, with a few exceptions. And this is our result, achieved with SAR-to-height. The original SAR-to-height framework input a single SAR intensity image, height reconstruction in slant range geometry, and then post hoc geocoding with range Doppler equations. This is our result. And I think you will agree with me, this is already orders of magnitudes better than the SAR-based result, for which 2 expensive satellites were needed. Here you need only 1 satellite in 1 image. This is SAR-to-height dual. Again, from my point of view, a leap in quality, because now the building's outlines are much clearer now and much more crisp, and the height's a bit more reliable. But here, this comes at the cost of needing 2 images from opposing views. But again, if we switch back and forth, it's definitely a certain improvement here to be visible. And then we have the SAR-former, in this case, single image. So, please recall, the SAR-former is capable of processing n input images from arbitrary acquisition modes and arbitrary timestamps and arbitrary viewing directions. This is the most simple case where we just say, okay, instead of using SAR-to-height, we want to use SAR-former, and we just use a single image as input. And you see that we also get a decent reconstruction of the scenario. And then this would be the result if you use at least 2 images to make it a bit fairer in terms of comparison to the SAR-to-height dual scenario. And here you see we have very crisp building outlines. We have very decent heights, and this already, just from a quick visual impression, is almost hard to distinguish from the LiDAR ground truth. And of course, since SAR-Former is a multitask learning setup that predicts simultaneously to the height map also building footprints, we can use the building footprints to filter this result and remove any pixels or any points that are not belonging to a building. And then this would be the cleaned result. You don't need any external data for that. You really can predict everything here from one single SAR image. And of course, this is equal to a level of detail 1, LOD1 city model reconstruction already, maybe even close to LOD2, because roof shapes are reconstructed as well here. And then, of course, we can again look at the LiDAR ground truth. This is the LiDAR ground truth, of course, with vegetation now, not filtered for buildings. But you see here there's, in many cases, great resemblance of the building structures. And of course, it's not perfect. And I would never advocate using SAR-to-height as an alternative to photogrammetry or LiDAR. I would only advocate using it if in rapid mapping scenarios. So if time plays a role, if money plays a role, if, I don't know, obstruction by clouds or smoke plays a role, then I would say you should use SAR-to-height. In any other case, if you have time and money, please still use LiDAR or photogrammetry. This is a clear message at this point. We also did an experiment checking out whether our model easily transfers to new space SAR data, because here we face something like a few shot learning scenario. Of course, we don't have as much access to ISI, Capella, and Umbra data as we have to TerraSAR-X data, but we received from these companies a few images each, and we used some of them for training and kept Berlin as an holdout set. And then we processed with our model these 3 images from ISI, Capella, and Umbra. And you see here in the bottom row that also these height reconstructions are quite reasonable and quite meaningful. So even in this, let's say, few shot setting, the SAR-Former provides quite powerful results based on the fact that it has awareness about the metadata and can easily transfer from one kind of data to another kind of data. And to exemplify this even further, we also went to a scene that is not, let's say, typical for the training set. So in this case, it's a rugged mountain scenario in Morocco. So if you recall, most of our training cities were more in the northern hemisphere and in the Western world, if you want, and clear metropolises. And here we have a city from the global south, and the terrain is also mountainous and not flat. And the question is, can we also reconstruct heights in such scenes that are less similar to the training set? And here, if we overlay our reconstructed heights, building footprint filtered to this SAR intensity image, we also get quite a decent impression of the distribution of building heights in Agadir, Morocco. And that brings me already to the summary and conclusion. I will keep this rather short. I would say that processing SAR data with deep learning is clearly not the same as processing optical imagery because of the mentioned peculiarities of SAR. And that means the black box use of deep neural networks does not provide optimal results. If you really want to get everything out of your data, you need to pair SAR expertise with deep neural networks, and then you will get best results. And of course, a part of the community may be a little bit misguided by the availability of Sentinel-1, which, for example, doesn't really have the problems with the geometric peculiarities because the resolution is so low in comparison to the high resolution data. The current state of the art, in my point of view, is a SAR-specific vision transformer paired with self-supervised learning, simply because this is also the state of the art in optical image analysis. The only difference here being the SAR-specificness. And while large-scale 3D reconstruction of urban scenes from SAR intensity images is enabled by such a transformer. So really, you don't need any radagrammetry, any interferometry, or any tomography here anymore. I believe that is also a nice basis for further developments in other downstream tasks. So it's maybe even a step towards something that you could call SAR foundation model, if you pair it with other downstream tasks as well. Thank you for your attention.
Thanks a lot, Michael, for this great presentation and these outstanding results. So there are plenty of questions, so I'm not sure we will have time for all of them, but maybe the hot topic, many people ask if some code or weights or any materials could be available to have some experiment, trials, or methods.
Yeah, thank you for this question. And I'm, of course, not asked this question for the first time here. Well, I'm a scientist, and I'm very much interested in open science. We have published all our papers in an open access fashion, so you can access all of them freely, even without preprints, or even the official prints are available freely. We also try to publish lots of data publicly. We have done so in the past successfully a lot. But in this very case, right now, no code and no model weights are available publicly. This is simply because we have received a lot of commercial interest, and we first have sorted out things internally, how to deal with it. Also, parts of our research were funded by industry, and it's a bit more complicated in this case. At some point, we will very likely publish some codes, most likely no weights. But it's not yet decided. So I have to be sorry here. Right now, no publicly available code and definitely no weights.
Maybe you can just answer about the data, because some people ask about the availability of the images.
Yeah. So the big problem to this day is that satellite providers, with one exception, and I will mention that in a second, have very complicated end-user license agreements, EULA. Everybody who has ever worked with any SAR data will have signed some EULA. And these end-user license agreements are typically relatively restrictive. So if you buy some SAR data, you are allowed to use it internally, but you are not really allowed to give it away to others. And this is exactly the case here. We have been provided with the many TerraSAR-X images from the German Aerospace Center under scientific proposals, and it's just not allowed. We are not allowed to redistribute the data. And the same is pretty much for every other data provider. There's one notable exception. I don't get any money from them. I'm not related or anything, but I want to shout out to Umbra, the American company, who is the first company I have ever seen to issue their data with a so-called CC BY license. So all of their data is publicly available in an open access manner once anybody has paid for it. And this is a great concept, and this would greatly contribute to further developments of deep learning to SAR imagery. And I hope this is an example to other companies as well, but I'm not sure. It's a very uncommon business model.
Okay, we also have some more technical question about the metadata block that you are using inside your different networks. So is it optional, or how do you make it optional, or do you always need to use it for the SegFormer, but also for the UNet framework? Can you say a few words about this meta token? Are these optional, or do you really need them?
It was basically hidden in the slides. These blocks are always optional. So all the ablation results I've shown is basically were meant to illustrate the benefit if you add these optional meta information blocks. And the whole story of my talk was pretty much, if you add those meta information blocks, building elements, you will get a better result. And better is a bit a matter of definition. Better can mean you have a better visual quality. Better can mean you have a lower RMSE or MAE error. Better can also mean that your model transfers better from one type of sensor to the other type of sensor. So it's very helpful, and I want to clearly advocate and advertise, if you train deep learning models for SAR, build such blocks and put them into your models in one way or the other, because the model will benefit from this knowledge. This is more or less the take-home message, if you want one take-home message.
Okay, maybe just a small comment. All the webinar will be made available, so you will have all this presentation if you want to listen to it again and the slides. So don't worry, I've seen some question about that, and of course you have all the papers on the web. So another question about the pre-processing of the data. Do you do any pre-processing, or what are the pre-processing steps that you need? Any calibration, normalization, and anything you could mention about this preliminary steps before feeding your transform?
Yes, we do some pre-processing steps here, and one of the core steps is pretty much histogram matching between a test image and the training set. So if we train a model on a certain training set, then we look at the, let's say, joint histogram of the training images, and then we want to make every test image as similar as possible in terms of histogram to this training histogram. This has proven to us as very helpful, at least in the older versions of SAR2Hide. I have to admit, I'm not even aware at this point whether SAR-Former still needs it, but this was a very important pre-processing step we always did. And of course, what you also should not do is using the original decibel values, because they are very different from sensor to sensor, from mission to mission, from image to image. You will have, the model will get overly confused. So you need to add some sort of classic standardization in the beginning, putting everything into the order 0 to 1 or -1 to +1 or something like this, to make the models, the input to the models numerically stable, so to speak.
Okay. Maybe another question about the accuracy of your estimations, specifically when you have very tall buildings. And I would add a small question about any uncertainty estimation about your estimation, depending on the number of images you have and things like that.
Yeah, I start from the back. We haven't yet added an uncertainty prediction module, but this is a part of our ongoing work. So on 1st of July, a new PhD candidate will start, and one of his tasks will be to add an uncertainty prediction module to the whole thing. The second point is, it was implicitly in the question, and I can say yes, the higher the building, let's say, the higher the error, to be very simplifying. Also, the lower the building. So if you have, for example, informal settlements, slum dwellings that are only, I don't know, 2 meters high, here we recently found that the model doesn't perform very well here, simply because it's very hard for a SAR sensor itself to observe these height changes and to distinguish individual buildings from one another. So we might face a sensor-specific or system-inherent limitation here, that simply SAR cannot observe this. It's not a problem of the model, but of the sensor, if you want. But then again, we also don't have a lot of training data, because there is no LiDAR ground truth for slum dwellings. So it's twofold. It's on the one hand a sensor-specific limitation, on the other hand a training data-specific limitation. And it's very similar for high-rise buildings. If you have too many high-rise buildings that stand close to one another, then they overlap in a chaotic manner, and the model has a very hard time, let's say, disentangling the different close-by buildings. That's a sensor and system inherent limitation again, but also our training set, of course, does not contain an unlimited amount of high-rise buildings. So these are the two problem cases. Anything in between is much better.
Okay. Sorry, guys, I will not be able to ask all the questions you had, but anyway, I think you can send some emails to Michael or to his PhD students. You have plenty of materials on the web and you will have the recording of the session. So I would like to thanks again to Michael for this great presentation. Thanks for the organizer. I think that will conclude this seminar. Thanks to all the people who attend this talk. Bye.
Thank you very much for attending and for your interest.